This is the final week for Activate and the last reading passage that you will encounter for practice. So I take this opportunity to again recommend that you read all the information at the top of the page or whatever precedes the passage itself, which this one doesn't have one, but whatever is there could give you important clues as to what the passage is about. Then read the entire passage to successfully answer the questions. Also, it is best if you read the question and then all the answer choices before you choose the best answer. This particular passage should make you laugh, given all the days that we missed last semester due to inclement weather. So let's read. The figure is beyond comprehension. Every year, 1 septillion snowflakes fall worldwide. As the crystals fall, they encounter different atmospheric conditions that produce snowflakes with different unique attributes. The more complex those conditions are, the more elaborate the crystals. Kenneth Liebrecht is a physicist at the California Institute of Technology. Along with the work of scientists at the U.S. Department of Agriculture's Agricultural Research Service, ARS, his research is uncovering new information about the magical world of snow crystals, information that has practical applications in such diverse areas as agriculture and the production of electricity. Snow crystals are individual crystals, usually in a hexagonal form, while snowflakes are collections of 2 or more snow crystals. Beginning as condensed water vapor, a crystal typically grows around a nucleus of dust. Its shape depends on how the 6 side facets, or faces, grow in relation to the top and bottom facets. If they grow relatively tall, the crystal appears column-like. If the side facets are short compared to the length of the bottom and top facets, the crystal looks plate-like. Currently, Liebrecht is trying to crack the problem of why the crystal facets' growth varies with temperature. He believes this may have something to do with the ice surface's quasi-liquid layer, which affects how water molecules stick to the surface. By manipulating the temperature and humidity within an incubation chamber, and by adding an electric current or various gases at times, Liebrecht creates designer snowflakes in his lab. Such experiments are helping him determine how crystals form. William Morgan, a retired ARS research biologist, and a colleague, Eric Erb, were using scanning electron microscopy to look at biological problems relating to agriculture. To avoid the laborious procedure that using such equipment usually entails, the 2 scientists decided to freeze the tissue they were working with and look at it in the frozen state. One day it happened to be snowing, says Morgan, and we were looking for a specimen. We imagined some snowflakes and were surprised to see what we did. It was the very first time anyone had attempted to image snow crystals with scanning electron microscopy, which provides precise detail about the crystal's shape, structural features, and metamorphose conditions. Crystals often change once on the ground depending on the surrounding environment. Morgan called another ARS colleague, hydrologist Albert Rango, to see if the snow crystal magnifications had any applications for his research. Rango now uses Morgan's electron microscopy data, along with microwave satellite data, in the snowmelt runoff model to predict the amount of water available in the winter snowpack. For western states such as Colorado, Montana, Utah, and Wyoming, about 75% of the annual water supply comes from snowmelt. Snowmelt water is critical to crop irrigation and hydroelectric power, as well as recreation and domestic water supplies, fisheries management, and flood control. Before employing the scanning electron microscopy results, the forecasted amounts of snowpack water were inaccurate whenever the size and shape of the snow crystals varied much from the norm. The more we know about crystals, notes Rango, the easier it will be to use microwave satellite data for predictions of the snow-water equivalent. Currently, forecasts using the model are about 90% accurate. A 1980 study estimated that improving the prediction by 1% would save $38 million in irrigation and hydropower in the western United States. Rango is also looking ahead at climate change predictions. Following the estimates that have been made about what will happen by 2100, things are definitely warming up, he says. Temperature increases will likely result in a reduction in stream flow as overall snow accumulation decreases, winter precipitation runs off as rain, and water evaporates at a quicker rate. The gap between water supply and demand will magnify even more, greatly increasing water's economic value, anticipates Rango. Not only does the crystal research help gauge snowmelt, it is also useful in predicting avalanches, designing artificial snow, and perhaps, in the near future, examining air pollution. You can put snow in a scanning electron microscope and tell which elements are present, such as sulfur and nitrogen, says Morgan. You can then see what kind of pollution is in the area and possibly track the source. Question 36 is a close reading question. You have to look back at lines 3 through 6 for the answer. The passage states, let's go over there. The passage states, as the crystals fall, they encounter different atmospheric conditions that produce flakes with unique attributes. The more complex those conditions are, the more elaborate the crystals. Therefore, answer choice G is correct. Falling snow crystals meet with varied atmospheric conditions. Question 37's answer can be found if you go back to lines 15 through 17. Up here. Snow crystals are individual crystals, while snowflakes are collections of 2 or more crystals. This means D is correct. Snowflakes differ from snow crystals because the flakes are composed, made up of, more than one crystal. Question 38 tells you exactly what line to go back to and read. It uses the term designer, just like designer handbags or designer sneakers. It means that these snowflakes are uniquely created by this scientist. Letter G is the correct answer. Question 39 also refers the reader back to a specific line in the passage, so reread the whole sentence containing line 59, just for clarity and context. So that's down here. Snow melt water is critical to crop irrigation and hydroelectric power, as well as recreation and domestic water supplies, fisheries management, and flood control. The word critical here means important, or its synonym here in letter C, vital. Question 40 is a broader question about the passage as a whole. It also has except in all caps, so pay attention to that word. Read all the answer choices. The only thing that this reading selection does not tell us that research is currently helping science do is F, extract, pull out pollutants from snow. The last paragraph tells us that scientists might be able to figure out what pollutants are contained or caught up in the snow, but it does not tell the reader that scientists are yet able to extract the pollutants.